Unit 4 Chemistry, Chapter 10 of your Heinemann textbook. We are now on to a completely new unit, and in this unit we'll be looking a lot more at the organic chemistry side of things. Much of this you will find familiar from Unit 1, although you may find that you've forgotten a lot of it, so some revision is going to be necessary. We're starting with looking at the structure of organic molecules and nomenclature, which is how we name them. All of these organic molecules are based on carbon, and they're based on carbon because it's unique in being able to bond with itself to make long chains or rings, and it can also make single, double or triple bonds with itself, but also with other common elements. So it can bond with oxygen, sulfur, nitrogen, hydrogen, metals in some cases, halogens, lots of things. Because of this, it is the basis of life. Okay? And you are based on carbon molecules, as is all living things on this planet. Okay? We also exploit these properties of carbon to make plastics, so polymers, okay? Colloquially called plastics, but you guys of course know that plastic is a property. Yeah? It is the opposite of elastic. It's when you bend it and it stays in that shape. Okay? We can make synthetic molecules with the properties that we want them to, but in order to do that we have to understand some chemistry about how structure influences properties. So, the simplest ones we're going to look at are your hydrocarbons. Simplest because they contain only two elements, carbon and hydrogen. Those can be arranged in a range of different ways. They could have single or double bonds. They can be in chains which are just one long line. They can be branched, or they can be in circles, ring structures. We put them in groups that are called homologous series. So each time you are adding to the homologous series, you're adding just one CH2 to the main chain. Okay? Doesn't mean you're adding a branch. That would be making a different homologous series. If we talk about a saturated hydrocarbon, which means we've only got single bonds between those carbons. Unsaturated ones will have at least one double bond or triple bond and might have more than that. So there's three different groups, homologous groups within this. Your alkanes, which are the saturated ones, they tend to be only used as fuels and they're really unreactive. Your alkenes, who've got a double bond, at least one. Okay? If they've got one double bond, then we've lost two hydrogens. So their general formula has two less hydrogens than the alkane with the same number of carbons in them. Or alkynes, which have got a triple bond in them. Okay? And again, because we've added in that extra carbon-carbon bond, we are reducing the number of hydrogens by two. Alkanes and alkenes, because they've got these double and triple bonds, which are reactive sites, those are much more reactive than your saturated alkanes. Okay. So this is an example of an alkane. Yeah. Can we name it? Hopefully we can. It's got 1, 2, 3 carbons, which means it's got the prefix pro. And because it's all single bonds, it's got the suffix ane, so it's propane. Okay. This one here is an example of an alkene. Now, same prefix, prop, okay, but because it's got double bond, it's now got a different suffix, a different ending, which is now ene. So this is propene. And then finally, we add that triple bond, we can now make the alkyne, so it becomes propyne. Remember when we're naming them, we first name the longest stem, okay? So the longest continuous chain of carbons, which they might draw funny. So they might draw it so it looks a bit bent, but just make sure you're counting a continuous chain of carbons. And then we have what's called our stem. I won't read all of them out to you, you're perfectly capable of reading that. The ending tells us what kind of carbon-to-carbon bonds we got. So if it's single, it ends in ene for double, and ine for triple. If it's possible to have it in more than one place, then we'll put a number in to tell us where it is. And that number says is the lowest number of the carbon it goes from and to. Okay. So here are some examples of alkanes. Yeah, those alkanes can also be arranged in ring structures. Okay, if we put them in a ring structure, then we give them a prefix cyclo. So here's our old friend propane again, and it's been arranged in a ring, so it's called cyclopropane. And notice that to put it into a ring structure, we've made an extra bond between two carbons, which means we've, just like when we did an alkene, we've reduced the number of hydrogens by 2. Okay? This one here, which you might be tempted to call 1,3,5 cyclohexane, don't call it that. We call it benzene. Okay? This is a special one. Okay? Essentially, each of these 6 carbons has got a single bond between them. But then they've also got an extra electron, which is delocalized around the ring. And then each of them has just one hydrogen on them. So this is C6H6. Whereas cyclohexane, where we've just got single bonds, is C6H12, because each carbon has got 2 hydrogens on it. It's a very stable structure as benzene. You'll find it is a very important molecule when we come to looking at some of our amino acids. Very nonpolar, almost entirely unreactive, but we can substitute the hydrogens that are on it for some other functional groups. We just can't break up this ring. So here we would have an example. Now in the case of cyclic molecules, our ring is our longest chain. So there's 4 carbons in a ring. So it's cyclobutane. And ane, of course, because it's only single bonds. Still staying with our hydrocarbons, ones that only have carbon and hydrogen in them, the other thing we can have is a branch. So many of them will have branches on them, and we name them according to the length of the branch and the position of it counted from whichever end is closest to it. So everyone knows it's a branch. We say a YL ending, and that YL ending, or IL, tells us that it's a branch, not the main chain. So you might have a methyl or an ethyl branch. If we've got 2 groups which are 1 carbon in length, then we'd say it's dimethyl. And then we also have the number that tells us where it is. So if we had something like 1,3-dimethylpentane, that would mean we've got a 5 carbon chain, which means, well, it's pentane. We've got 2 methyl groups, dimethyl, and remember a methyl group, meth, it means 1, so we're going to have 1 carbon in each of those. And they're going to be 1 on the 2nd carbon and 1 on the 3rd carbon along the main chain. Okay. If we look at this one, 1, 2, 3, 4, 5, 6 in the main chain. So this is hexane. Okay. Here we've got a methyl group. So this is 1 carbon off the main chain. It's not 1, 2 in total. We already counted that as part of our main chain. Here we're counting this 1 extra. And it's on the 2nd carbon along. So this is 2-methylhexane. And we need that 2 to tell us that it's not here, because that could be 3-methylhexane. Wouldn't have a number if it was here, because that would then turn it into heptane, because it would be on the end, and you can never have a branch on the end, because that's just extending your main chain. Another example. Okay, this is the one we were looking at before, 1, 2, 3, 4, 5, so pentane. Okay, here we've got 2 methyl groups. Okay, they're the same and they're off either side, so you might be tempted to think of this as 3 in a row. But again, we already counted this middle carbon, so these ones are separate from it. So they're both methyl groups, so it's dimethyl, and they're both on carbon 2, so it's 2,2-dimethylpentane. One last example. Here looks a bit more complex. First thing we've got to do is figure out what our longest chain is. So 1, 2, 3, 4, 5, 6 is looking good. Okay, let's just check some of these corners. We can go 1, 2, 3, 4, 5. That doesn't help us. 1, 2, 3, 4, 5, 6. Okay, we'll stick with 6. So it's hexane. Okay, we've got up the top here 2 methyl groups. And down the bottom here, 2 ethyl groups. I'm going to talk about my ethyl groups first because E comes before M alphabetically. And that is how it works. So I've got 2 ethyl groups, okay, 1 on carbon 3 and 1 on carbon 4. So it's 3,4-diethyl, 3,4-dimethyl hexane.